It's a dude here. He's coming early when he gets back.
In a big empty room, you cluster together.
We're looking forward to having him.
I can equally space them out.
It's weird. It's just like completely nuts. But it gives me back too.
Yeah, 5 minutes in. I remember 5 minutes in. Though I don't know if we discussed CMBS4.
There we go. There was like not a lot of people signed up for that. It stands right now.
Oh, okay.
People
Start
don't
some.
go out on Friday night. That's a great
It's a
time.
new space. Yeah.
We're going into Sounds like that would be a
Carol.
PhD.
Carol?
Okay, so thanks everyone for coming. Today we have Gil Holder, Sure. So he's going to tell us a lot about the CMB and the kind of astrophysics that we can still do with the CMB. But I guess he's in the past been interested in problems related to dark matter and dark energy, and worked in really a diverse set of subjects, I'd say, from gravitational lensing, CMB, early universe physics, to even like solar system physics. So yeah, I think there's a broad interest here that people might want to talk to him about different ideas. He got his BSc and MSc from Queen's University, and then moved for a PhD at Chicago. But now he's, I guess, a few hours away from Chicago, professor of astrophysics at Illinois. And without further ado, yeah, I'll let you take over.
Great, thank you very much. So yeah, it's nice to be in a part of the world with a little bit of contour. So Carol was talking about how Cambridge is very flat, and I'm like, you don't know flat. Urbana-Champaign, now that's flat. So it's good to be back here. I think I was back just before, I was here before COVID, and so it's interesting to see people again. So what am I going to talk about? So it's a bit of a grab bag. So I'm going to talk about some CMB lensing, and then talk about some stellar flares. So we've actually found some really strange things in our data. And then I'm going to start looking forward for Kinetic SZ. So and just as an example, I'll point out that we could use this for something like helium reionization. So if there's people interested in that. And then looking even further into the future, there's a fun thing of polarized Kinetic SZ, which I'll explain to you, and hopefully you will get excited about it, and we can find a way to build something that can detect it. All right, so it's the CMB. So here's where we are in terms of the CMB power spectrum as of a few months ago, or maybe a year ago. So you see there's the temperature power spectrum up here. So this is the angular power spectrum. So you see the Planck points are out here, and then the ground-based experiments take over. And you see we're going out to L of 3000. So this is a scale of maybe three-ish arc minutes are the scales out here. And what you can see is that it's extremely well measured in temperature. And in fact, as you get to smaller scales, as we will see shortly, it starts to get confused by foregrounds. We start to see a lot of galaxies and things like that. So it gets to be tougher and tougher to do cosmology out here in the temperature. But you see here, there's the polarization power spectrum. So these are the E modes. And so again, Planck does very well. But you also see that there are actual measurable error bars on these points. So that's a sign that there's still lots to improve out here, that we could actually keep measuring this out here. And on top of that, the polarized foregrounds aren't as bad as the temperature foregrounds. So there's hope that we could actually keep going to smaller scales in polarization. So these are the E modes. If you look at instead the B modes, so the curl pattern of polarization, so now you see there's interesting new signals down here. So you see this is R. So this is John Kovac is spending a lot of time trying to figure out what the value of R is. And so the bicep Keck points are down here. And then you see there's ground-based points, and now you see the error bars are still pretty big. So there's still lots of work to do in CMB polarization, and there's lots of room to push down to smaller scales. So when people say what's left to do in the CMB, there's tons of discovery space out here in small-scale polarization, and then also, getting better out here and pushing towards trying to detect these gravitational waves from inflation. So there's lots to do in the CMB. Just in terms of pure CMB science. So I'm not going to talk about the pure CMB science. What I'm going to talk about are the other things that we can do now that we have these extremely precise measurements, especially on small scales. Okay, so here's to orient you on what the various CMB experiments are. So this is from the SNOMAS white paper. So I'm going to talk for the first little bit about SPT 3G. That's something that I've been working on. I've been working on SPT for many, many years now. It's hard to even think about how long I've been working on it. So we're operating, and we'll be going till something like 2024. Maybe it'll keep going a little further. Advanced ACT, so they're just shutting down. So these two experiments are measuring sort of arc-minute scale fluctuations in the CMB. Bicep Keck, and bicep array, so so John Kovac is doing a lot of that work. So that's large angular scales, so that's degree scale stuff, focused on going after that R signal. So these experiments are ongoing. This one's just shutting down. So the next big thing that's coming online is the Simons Observatory. So lots of people are members of the Simons Observatory. So that's kind of the next generation, which is basically starting imminently. And then looking a little bit further forward, there's CMBS4, which is a much bigger scale. So it's a joint NSF DOE thing, and it will be a mix of degree scale stuff and arc-minute scale stuff. And then looking even further forward, so then there's satellite missions, and then looking further forward, there's stuff like, okay, well, what if we could just do a super high resolution CMB experiment with a nearly infinite number of detectors, and so we can name it something, so we can call it CMB-HD. And so it is a proposed concept, but it's ambitious. So, but it's fun to think about this stuff. This is the Institute for Theory, right, and Computation. So we should be thinking about the stuff we can do out here as a way to drive instrumentation. What was that? You never know, cryogenics. Maybe we'll take a little gap right about here. So SPT ends right here, so maybe I'll take a little sabbatical here, deep freeze for a few years, and then come back. All right, so I'm going to talk about the South Pole Telescope for the first little while. And so we're now on our third generation of South Pole Telescope camera. So we're now on, it's creatively called SPT 3G for the third generation. And so we started with around 1,000 detectors, and now we're up at 15,000 detectors at 3 frequencies with linear polarization, so Q, U, and intensity. So this thing is a 10-meter telescope, and it's down at the geographic South Pole, and the angular resolution is roughly arc-minute. So those are the numbers to be thinking about. So what can we do with this? So we can survey lots of the sky. So just to give you a sense of where we're looking, so it's at the South Pole, which means we can only see things in the southern hemisphere. So the main survey footprint is this thing that you see here in orange. So we're kind of around 0 in RA, some range in kind of mid-levels of declination in the south. So that's the main survey, and this is roughly where BICEP is in the middle of it. So by design, we're working together, observing the same patch, and that'll help us measure gravitational waves. Now, it's also the case that there's a few months, 2 months of the year or so, where the sun is kind of awkwardly close to our main patch, and so we then look at other places. And so there's these other spots. There's one kind of clear on the opposite side of the galaxy over there, and then there's chunks over here where we're not quite as deep, but we actually have lots of data there. So for some of the science that I'm going to talk about, where you don't need to be super deep, there is discovery space out here. We could be discovering all sorts of interesting events out there. Now, so this might not mean much to most of you, but so let's see. So at the end of 2020, that was the last time we published a paper on this stuff. The temperature noise was something like 5-ish micro-K arc minute. And so that was, and then you see at 220, we're a little bit noisier. It's more like 15. So this is actually, so CMBS4, when they're talking about the large survey with CMBS4, the numbers that people talk about are more like 1 or 2. So, so we'll keep integrating down, and we'll get almost down to the level of the CMBS4 levels of noise once we're done, but it'll only be in this one patch of 1,500 square degrees. Okay, so here's an example of a map. So let's see. So this is a chunk of sky, 3 degrees on a side. This is what it looks like in Planck. So if you were to look in the Planck maps, this is what you see. And then if you instead look at what it looked like in SPT Pol, so the previous generation of camera, you can see a whole bunch of things kind of pop out into existence here, right? You see there's a lot of extra structure. And this is just saying that there's a lot of small scale structure that Planck just doesn't see. So there's lots to do on small scales.
Are the white spots SZ from clusters?
The white spots are mainly AGN. So the white spots are what we call point sources. So they're mainly AGN. Some of them are dusty galaxies. If they're dusty galaxies, they're probably strongly lensed. So I don't know, you can't tell by looking at them. They all just look like white dots at our resolution. But that's a cluster right there. That's SZ right there. So if we ran a match filter on this, we'd find a whole bunch of them popping out. Boy, this is a sufficiently dark spot. That might be a really nearby cluster, but it would have to be nearby. Yep.
I'm seeing these vertical white rivers.
Yeah.
Is that real, or is it an artifact of the imaging?
It's real structure.
It is.
And what's happened is that the way we scan is we scan back and forth across the sky, and we're at the South Pole. So the sky doesn't rotate, it just kind of revolves, or I don't know what the word is, but it goes around, it doesn't rotate. And so when we scan back and forth along lines of constant elevation, so we don't go through too much atmosphere changing, that means we're removing a lot of the structure in the horizontal direction. So our filtering removes more of the horizontal structure than vertical structure. And so because of that, you see a little bit more vertical structure than horizontal in the maps. So it's real structure, but you see it because there's the absence of the horizontal structure that we've removed. So that was with SPT Pol, and now with the new camera, we can do the same patch, and then what you see is basically all the noise just goes away at the level of this plot, right? So here we are. We've basically gotten rid of the noise as far as you can tell. So now you can really see not only that cluster, but it's got a little buddy right there. So that's actually 2 clusters right next to each other. And then you see all these dots. And so there have been a multitude of papers written on the clusters. So it's a great way to find clusters. So this is an interesting way to find clusters. It's a Sunyaev-Zeldovich effect. It's just upscattering. And then, these sources, finding out what they are. So most of them are AGN. So there's lots to be done with those as well. So I'm not going to talk about that astrophysics today, though. All right. So this is what I'm saying. So like with these maps, you see these, these rivers. I really like these vertical rivers. That's good. And then the dark spots and the white spots. If you look at the references to SPT, the citations, what you see is we're actually getting something like, a third of our citations are coming from those dark spots. A third of them are coming from the CMB stuff, and a sizable fraction are coming from the subset of those galaxies that are actually dusty star-forming galaxies. So it's not a new idea that these CMB surveys are actually astrophysical surveys. So this has been ongoing for a while. Now, what I'm curious about is, so this is great, we've done all this stuff, but what other stuff can we do? So I'm assuming that the clusters and the submillimeter galaxies and the AGN, these are topics where people are thinking about them and moving them along. So what else can we be doing? So as an example, we can do gravitational lensing. So just to see how this works, here's a patch of the Planck sky. So this is Planck, and it's centered on the North Pole. This is what the North Pole looks like in the millimeter. And now I'm going to drop a lens in here. I'm going to simulate a lens. I'm going to drop it down, and it's going to be about 10 times larger or so than a real lens would ever be. But just so you can see how this works. So this is what CMB lensing looks like. So this is 20 times larger than is typical, so this is just so you can see it. But notice that what's happened is that you can look at this map and you can say, that spot looks funny, right? Why does it look funny? Like it doesn't have a different mean, right? It has the same mean as all the other spots over here. If I just kind of take the average in here, it's not going to look any different. But it's just like, it looks funny, right? So what's wrong with it is that in the middle, the spots are too big. So it's basically taken the power spectrum of the CMB and it's skewed it towards larger scales. So now there's too much low L power compared to high L power. So it's messed up the typical scale of your fluctuations is one thing it's done. So this part looks funny because everything's the wrong size compared to everything else. And then this stuff looks funny because it's been sheared out. And so what does that say? Well, that says that the typical fluctuations have this orientation to them in this region that these ones don't. And so what you're doing when you do this is you are basically looking at the breaking of statistical isotropy, right? The statistics are different at this part of the map than they are out here. So it's still a Gaussian random field. Like if you were to do this 1,000,000 times and histogram up the value of the CMB at that spot, it would be the same nice Gaussian. So it's not exactly non-Gaussianity, although we call it non-Gaussianity. But it's a breaking of statistical isotropy. And so you just look for spots where the statistics are wrong, which means you have to do the statistics. So you basically, so the way you can reconstruct the lensing is you just say, well, how much has the power spectrum in this part of the map been shifted? And that's telling you how much lensing happened. And you say, how much is the power spectrum here anisotropic? And that tells you how much shear there is at this spot. So this is how you do a lensing reconstruction. And so people use words, quadratic estimator is the word that people use. And when they say quadratic, they mean something is squared. And when they say something is squared, it's because you're looking at how the 2-point correlations are varying across your map. So obviously this is not exactly the way we do it. We're not going to just take the power spectrum and look at it. You do something optimal. But in general, when you do an operation and you could say, oh, well, there's a lens right here and it looks like some spherical thing that then is compensated, and you know it's compensated because everything just outside looks fine. So that's how CMB lensing reconstruction works. And so we're doing this on the 3G lensing. So right now we're working on the 2019-2020 maps, and you'd say, wait a second, isn't this 2023? How is it that you're only working on 2019-2020? Well, so we thought it'd be good to do something quick. And then it turned out not to be quick. So COVID hit, so that didn't help. And then on top of that, one of the problems is we're so much deeper than we were before that actually we just see a lot more of those white dots, those point sources, those AGN. We're just seeing a lot more of them than we knew about before. And so there's kind of been iterations of figuring out how to mask them and things like that. And it's just, stuff takes time. So hopefully this will be out. We're aiming for summer is kind of where we are now. And I think that's realistic. So just to give you a sense of what the quality of these reconstructions are. So here's one of our simulations is based on, real noise based on differences of our time streams. So here's what we expect we should be able to reconstruct. So this is a simulation. And then if you just subtract out what the signal is in the simulation, you're left with pure noise. And what you see is that we're clearly seeing some we should be being able to do some decent reconstructions of CMB lensing. Now, I told you all the stuff we have. So we have 90, 150, 220 gigahertz. So 220 is a little noisy for this, so mainly it'll be 90 and 150. We can also use both temperature and polarization. So we have all these cross-checks where you can say, remember I said that you're doing the two-point statistics. Well, you can take two-point statistics from different frequencies. You can do temperature and polarization. You can do, you can mix and match from this whole matrix. And that's another reason this is taking surprisingly long, is because you're like, well, let's cross-check it this way and cross-check it that way. So there's kind of a whole matrix of things you can do. Well, I'll actually say what's going on in a second. So here's how well we should do. So there's two different ways to think about lensing power spectra. So this one up here is the CMB lensing. So this is the kappa. This is the lensing convergence between us and the CMB. So this is the whole universe between us and the CMB. The lensing convergence. So there's the theory spectrum, should look something like this. So Planck has measured this, made a map in the same way, and that's the noise power spectrum in Planck. And so what that means is that in a typical, in the Planck map, on degree scales, if you pick a spot, it's as likely to be signal as noise. But, that's still pretty good. Whereas with SPT, we're going to be at the point right here on degree scales, we have 10 times lower variance in the noise as compared to the signal. The signal is a Gaussian random field. The noise is a Gaussian random field with 10 times lower variance. So this is what we're building. And, this is what the curse of high signal noise is, you actually see stuff that looks funny. And so we're working on it. So the way it often gets cast is in terms of errors on the power spectrum. And the thing is, we only have 1,500 square degrees. So with only 1,500 square degrees, even though we have much lower noise, there's just sample variance on the particular draw of the CMB. So if you look at the error bars on the power spectrum, it's, when you get out to L of about 200 or so is where we cross over with Planck. So we'll be doing much better on these smaller scales compared to Planck. Now, ACT has lower noise than Planck and has much wider area than us. So I think that the ACT experiment should, as far as I can tell from looking at what they should be able to do, should have substantially lower error bars than us. So that's why I think of this as we're making a map of the lensing, and it's going to be a great map. Yep.
Is this after removing the point source down?
Yeah.
Flux, so there
Yeah.
must be a sensitivity on the flux that you remove it down to.
Yeah. Well, so there are tricks you can do on the point sources. So for one, the point sources aren't as obvious in polarization. So for the most part, they're only a few percent polarized, whereas the CMB is 10% polarized. It's especially sensitive. So when you do the temperature reconstruction, the point sources are really nasty. So there are tricks you can do where the point sources have an anisotropy that's different from a lensing anisotropy. And so it's called bias hardening. So you can actually do, it's not as bad as you can think. You can kind of diagonalize away most of your point source trouble, and you pay a small hit in signal noise.
If you do two frequencies, you can kill it. You can
Remove them more easily.
Well, you would think that, yes. Right, so Avi's suggesting multi-frequency removal. The problem is that every point source is a snowflake. So every AGN looks a little different from every other one. And dusty galaxies, while they all look roughly thermal, they all look a little bit different. Each one's at its own redshift, and it has ever so slightly different emissivities. So you can get rid of 90% of the trouble by using the spectral information. But then that 10% that's left is frustrating. Yep.
Well, we're on the subject, so how about diffuse photograms? Have they heard it all at this point?
Dust, polarized dust, say.
We have no troubles with polarized dust. Yeah.
Simply angular scales?
It's mainly the angular scales. I mean, we have a real hard time seeing angular polarized dust in our field. So you guys are sensitive enough that you're more sensitive than we are. So and it took you a long time to get to the point where you could see the polarized dust, right? So we have no evidence that we see the polarized dust. And then what we can do is you can take some template for the polarized dust and fold it through and see how much it screws up the lensing. And for us, it's not a big deal. So our lensing is dominated by L of 2 to 3,000. So it's not so, well, I guess it's L of 1,000 is where the E modes are peaking. So hopefully, it seems like we don't have polarized dust problem, but we have not actually, I haven't proven that. So before getting my Nobel Prize for this, I'm going to have to definitely check for dust.
It'll be relevant for forecasting for S4 levels.
Yeah. Well, and S4 is going to have a problem because it's looking over a lot more sky. And so we're looking at a pretty quiet part of the sky, whereas S4 is looking at more, dirtier spots.
Gil, another question on this. So you're doing this measurement statistically across your entire region.
Yeah.
The example you gave, you said, was exaggerated, of course.
Yeah.
But it seems like if you had some sort of an image-based search technique for this, you might be able to identify individual regions where you have particularly strong lensing. Is that something?
Well, yeah, I mean, we have a map, right? I mean, that's what this map is. Well, not this, sorry, this map. This is actually this is the current map. This is our current best estimate. So we're pretty sure you can't do anything with this, especially with this point source sitting there. That's the thing we call the focus quasar, and it's so bright we actually forgot to mask it. Yeah, but like these are real spots. Like these are spots where there is anomalous lensing going on. And if you look at the guts of what a quadratic estimator ends up doing, most of these end up being you do some filtering, and you basically then just multiply the two maps. So this really is while people do all the math in Fourier space, if you actually were to keep track of the properties of convolutions in one space versus multiplications in the other, it really does turn out to be just multiplying two maps together, and that is going to pick out spots that are weird. And that spot's weird because there's a bright source there. So yeah, and so we have a map, and in principle you can look for spots that are weird, right? You can say, you could do the kurtosis of this map, and you could look for stuff out in the tails. You could do a one-point distribution, and you could look. So this is the kind of stuff that I think is good for astrophysics, especially. And one reason, so for instance, this is everything between us and the CMB. And so you could take the same map done with a cosmic shear experiment, and they've measured everything out to, say, redshift 2. And for me as a cosmologist, it's like, redshift 2, don't we know that stuff already? Let's take that stuff out. And then you have a map of everything behind. And this is where it really helps to have a low noise map. So if you did this with the Planck map, you would remove the stuff that's in the foreground, then you'd have a still noisy estimate of whatever's there in the background, and the signal's going to be lower. So here you can take the foreground stuff out and still have decent signal noise on the stuff that's in behind. And that's where you could start looking for correlations with clusters, with high redshift quasars and things like that. So that's why I think the astrophysics is going to benefit a lot from having a low noise map. So that's the plan. And so this is where we are on this map. So as I said, this is just 2019, 2020. So we'll be, by the time we include out to 2024, we'll be more than a factor or root 2 deeper in the temperature and polarization, which should be more than a factor of 2 in the lensing. So we're going to have very high signal noise maps, which will be great for looking for interesting spots in the universe. All right, so we could also delens. All right, but let's change gears. Here's something that was surprising. This is the coad of all the 2020 data right here. This is all the data from 2020, and this is an RGB image. Red, green, blue is 915220. And what you see is it doesn't really come out on this screen, but you can see this kind of ghostly stuff in the background. That ghostly stuff in the background is the CMB. And then these dots are basically AGN. So, but the way we make these, we just scan the sky over and over and over again, continuously. So relentlessly, I guess, is the word that the bicep Keck people use, relentless observing. So, for 8 months of the year, we just go back and forth over the same 1,500 square degrees multiple times, roughly once a day, but sometimes more often, sometimes less often. So here's one particular 2-hour observation in 2020 that went over this patch of the sky. And now we can just say, what's changed? So, well, this one looks a little dim, so maybe this is probably might be a time variable AGN. but what the heck is this thing? Yeah, well, if I put a little crosshair on it, you'd think it was a supernova, right? Judging by all the old talks. Yeah, so it could be a supernova. Who knows what it is, right? But it's weird, and here's like literally the next day.
So it's not a supernova.
So it's not a supernova. Well, or it's a really interesting one. If it was, well, it could be an FRB as well, but it would, it'd be something that was some number of millijanskis and some number of minutes of observation. So it's the brightest FRB ever. Right. So it's like, what the heck is that thing? But also notice how bright this thing is. It's bright. Like, these are bright sources in our map. You can see them by eye. And this thing is just, it's comparable to that. It was there for a day, one observation, and then it was gone. So the other thing that I like about this plot, though, is you can actually see the same sort of structures from, the CMB structure. You can actually see it in these individual 2-hour maps. Just a little faint background that we're imaging the CMB in 2-hour observations. That's how deep these cameras are. Okay, so what are these things? Well, so here's another one. So this is one. So I have a student at Illinois, Chris Tandoy, has been digging in, really trying to figure out what these things are. So here's another one. One day, the next day, then it was gone. So here's the time stream. Here's we actually have, remember, like 8 months of data each year that all look like this, right? Where roughly once a day, we'll have some measurements, and then, oop, there it is. It went from undetectable, down near 0 up to 80 millijanskis, and then went back down again. And then you can zoom in on this, and you see that because we go back and forth over it as we go, we can actually see it over a few minutes. So here, this particular source, we see actually went up in a few minutes and then decayed in a few minutes. But then the kicker is if you just go to the Y's, you just stack in Y's, you go to the Y's and you just say, well, where is this object? And you see it's centered right here on this thing with the crosshair, which is a diffraction spike on a bright star. So what these things are stars. They're flare stars. So here's another one. This is the craziest one. This is the first one we saw. So actually, Alan Foster was at the pole, and I guess, so he babysits the telescope. We have 2 guys down there, and he just would go through the data and just look, noodling around. And he's like, what's that? And so at the same time, a Berkeley postdoc was actually writing a pipeline specifically trying to find these things. And then he ran his pipeline and said, oh yeah, here's what it is. So the two of them, so it was Sam Guns was writing the pipeline, Alan was down at the pole noodling around in the data, and then my student Kale was doing some support. And so what this is actually 2 flares. So there you see, we have all these observations, and then boop, that's right here, that's a zoom in, and back down, and then boop again, hundreds of millijanskis. And then this object has the name, not only does it have a name, not only is it a star, if you know anything about stars, it's Z Ind. If it doesn't have just some phone number, that means it's super bright. If it's not identified by RA and DEC, that means it's really bright. So this thing is like 8th magnitude or something like that. Super bright. So this one is, I think this one's out a couple hundred parsecs. So they're all within a kiloparsec. So we'll get to that in a second. So yeah, so they're stars. So we look, and it turns out basically all of them, there's one that we're not quite sure of, but they all seem to be stars. Some of them go off multiple times, like this one did, and then CC went off. This one was kind of disturbing because it actually, we've marked the flares. It kind of flared a little bit, and then it flared a little bit more, and then it flared a little bit more, and then it flared a little bit more. And Avi sees this and probably thinks that they're coming for us, right? But then it didn't get even brighter. So it's not something that's actually coming towards us. So we're okay. So we have time resolution. Some of them actually are resolved in time. They're not all. Some of them just look flat and something like this. But I just want to remind you, well, maybe not even remind you, but so here are the galaxy number counts with SPT. So this is from Wendy's paper, Wendy Everett. So these are the numbers of galaxies per square degree above some flux. And this is labeled at 220 gigahertz in Janskys. So this is 220, but, and you see that here's a Jansky. And you see that we're running out of sources in our survey at a Jansky. So when this thing turned on, it was comparable to the brightest source in our entire survey for those 10 minutes of glory, and then it just went away. And what's crazy is this has been going on ever since people have been measuring the CMB. They've been scanning back and forth, writing down numbers, adding them all up at the end, and every once in a while, the brightest thing in their map was actually one of these stars, and then it would just disappear. And no one noticed until someone looked. So these things are super bright. Okay, so they're all stars. So what stars are these? So these are the ones that we found matches to in Gaia. There's 66 of these. So this is the latest. This is from up to 2022. So this is an HR diagram. We have color. We have the magnitude. And so what do we see? We see they're all over the place, right? Some of them are way in extreme. Well, I would call these extreme. Maybe Ito wouldn't call these extreme, but lots of M dwarfs down here, and then lots of stuff up here in the giant branch. They're all over the place. So you can compare it to just the general distribution of stars in Gaia, in our patch, and you see that it doesn't quite trace what typical stars are. We have too many down here, too many of these faint red stars, and there's not very many stars in here, which is where most of the Gaia stars are. And in fact, I personally suspect that these two are probably false associations. But yep.
It's quite remarkable because you're saying that 10 to the minus 4 the solar luminosity is in a flare at 150 gigahertz. That's huge amount of energy.
Yeah.
I mean, the sun. What is happening in the sun?
So the solar flares are typically maybe 10 to the 4 times smaller. A solar flare would be down in these units, I think, around maybe 10 to the 23.
But the sun is very inactive. M dwarfs in the X-rays can produce flares that are 1% of the volumetric luminosity.
But these are not M dwarfs, are they?
Well, so these ones we think are M dwarfs.
Okay, but the
Well,
ones above?
These are, so some of them are, no, these are giants.
Oh,
So the only ones that are, so sun-like is right here.
yeah, but the sun will evolve. Okay, so yeah, but you see it all over the place.
Yeah. So it seems like a lot of them are binaries. So it seems like a lot of these ones are binaries. Like, at least in Sinbad, they're labeled as binaries. And a lot of these are thought to be binaries. What's interesting is almost all of them are known to be X-ray active. And most stars are not X-ray emitters. So that's telling us something about what's going on. But it's very curious. So this is completely unexpected, and we're all cosmologists, so we don't know what to do. So if anyone has ideas, so we know what the stars are, but as Abby says, these are huge energies. Like, fractions of a solar luminosity are coming out for 10 minutes or so. So I'll give you a few more hints, and then you can tell me what to do with them, and then we'll move on. So there's a lot, so we can do a luminosity function. But here's the funny thing. So here we have 9150 to 220, so we can actually do spectral indices. So this is the spectral index from 150 to 220, where it's defined as alpha positive is rising. And here it is from 95 to 150. So this is just saying what's the energy at 90 versus 150 versus 220. So if the spectrum looks just constantly rising, you're up in this quadrant. If it's falling, you're down in this quadrant. If it peaks at 150 and then falls, you're over here. And if it has a valley and goes up, you're over here. So something's going on with that one. But what you generally see is that for the most part, like this line right here means just a single spectral index that explains everything. That for the most part, it's not too far off this line. And it's just this gently rising something like alpha of 1. So so it's not thermal. Thermal would be like 2 or even more if it had a different emissivity. It's not synchrotron. It's not optically thin synchrotron, or you'd expect something that's falling. And in fact, if you look at all the literature on radio flare stars, they assure us that it's definitely falling. All the literature says that these points should all be down here. So we don't know what the mechanism is. There's something weird going on in what the emission mechanism is. And maybe there's selection effects baked in here, but so this is the first mystery, is what's going on here. So why is it rising?
So do you have an estimate of the brightness temperature? Assuming that it's coming from something the size of the star?
Must be smaller because the duration is only a few minutes, you said, right?
I'm just trying to so I don't know that number
It takes more than a few
offhand.
minutes to cross the star at the sound speed.
So I've done
Right?
these,
It takes half an hour to cross the star at the sound speed. So it cannot be hydrodynamic.
No,
Across the
I'm
entire
just
set.
thinking, what are the temperatures
But
involved?
it could be a hotspot.
Yeah, instead of saying something wrong, I'm going to just go check. Yeah, we played around with
No
that.
hint that it's a coherent process.
There's no way it's coherent.
Okay,
yeah,
yeah,
yeah.
because you've got emission throughout the whole time, yeah.
Yeah, there's no way this
Yeah.
thing's
It
coherent.
must be pretty hot, that's my guess.
Yeah, so the thinking is it's probably something just that's very hot.
But it's binaries, you think, or
Some of them are binaries, but the M dwarfs are probably just M dwarfs. Some of the M dwarfs are probably just M dwarfs doing weird things. That's what we think. All right, so there's one more little hint for you to chew on, which is, TESS just does these sectors where they'll look somewhere for a while and then look somewhere else. So that means that they actually caught a couple of our flare stars when they were going off, when you go back and you look. And so here's the TESS, all these points right here is TESS. This is optical. So you see, and it's subtracted off the mean in this case. So subtracted off the mean, you see a couple little flares, and then something happened right here in TESS. And oh my goodness, that's exactly when our data was there. So it's at least not invisible in the optical, which is good. If it's putting out that much energy, something should be going on. So you see it's almost perfectly coincident. You zoom in on this and you look at our individual scans, and you see TESS was on a little earlier, and then it was decaying for a little bit longer, but the peaks are pretty close to each other. So
How much energy was in optical versus radio?
yeah, so that's, so what we did is, if you actually just look at TESS and convert it into, say, millijanskis. So this is the TESS-like curve in millijanskis, and you see it goes from 30 up to 50. So the optical flare was something like a factor, not quite a factor of 2.
In millijansky, but you need to
In the-
multiply by the frequency.
Yeah.
Yeah.
So that's,
So
but first I just want to say that, notice that the optical flux has not quite doubled. So it's a huge amount of energy compared to what the star has, is what it's gone up by. And then here we have, again, in millijanskis, and you see that the TESS flux is something like 10 times lower.
times the
So,
frequency.
right, so it's 20 millijanskis in optical, and it's 200 millijanskis in the millimeter. So now I need to know how many hertz are in an optical.
10 to the 15. So you
Yeah.
have 10 to the, you have 150.
Yeah, so
Gigahertz.
150 gigahertz.
So it's about 1,000,
Yeah.
right? So
So it's
1,000
about
times
100 times more is coming out in the
in the optical. Yeah, so it's mostly the optical.
Yeah.
Yeah.
So we're getting about 1% of that flux is coming out in the millimeter. So something's going on, and we're not quite sure what it is. But TESS is going to be back in our main field this summer. So hopefully we'll get a couple more of these in the summer, and we'll have coincident optical imaging for our flares. And if we can figure out a way to get someone else on it, that would be great. So, all right, so that's what we got so far. All right, so there's a few minutes left. Let's talk about some of the other crazy things we can do. So here's the map. So, there's the dots in there, but there's also the fuzzy stuff. So something you can do is what I'm going to call kinetic Sinyaev-Zeldovich effect tomography. So how does that work? So let's say you have a bunch of galaxies somewhere. There's my galaxy sample. It's not real, obviously, but there we go. Now I'm going to have all of them moving this way. So I have this whole cloud of galaxies, this collection of galaxies is caught up in a cosmological bulk flow. It's sliding this way. Now, any galaxy is not just a galaxy. It has its little cloud of structure and, in particular, electrons around it. So here are my clouds of electrons. that go along with every galaxy. So that's some combination of a 1 halo and 2 halo term, like, it's the large scale structure. There's going to be an excess of electrons associated with each galaxy. So I have an excess of electrons that are all caught up in this bulk flow. And now there's this CMB that's around. So the CMB impinges in all directions, and it's going to scatter, right? A few percent of these electrons, well, not quite a few percent, maybe 10 to the minus 3 of the photons coming in are going to scatter off some electrons and go in some other direction. And so the ones that are going in the same direction as the velocity are going to get blue shifted. The ones that are getting backscattered are going to be red shifted. So if you look from over here, and you look at this collection, what you're going to see is you're going to see a bunch of galaxies. And where the galaxies are, you'll also see some little cold spots in the CMB. If you look over here, you see the opposite, right? You see galaxies, but now you're going to see hotspots in the CMB. So what that says is that by looking at how the galaxies are correlated with your CMB map, you actually have an estimator for this bulk flow. So we have a way of estimating the large-scale bulk flow that these galaxies are caught up in by looking at how the CMB map is correlated with our galaxy map. So that's our estimator of the velocity. And so that, right, we have more electrons near galaxies, CMB scattering off of this bulk flow, and then this CMB is either going to be correlated or anti-correlated depending on V. And now the amplitude of that correlation depends on the bulk flow, but it also is going to depend on the clouds. The more electrons we have, the larger this signal is going to be. All right. So what can we do with this? Well, so now we can just go find our favorite galaxy survey. And so here's a slice out of BOSS. And what this says is that here you see some overdensity here and some underdensity. So you could use this survey and use that to cross-correlate with your CMB map. The other thing you can do is you could actually use this survey to do a velocity field reconstruction, right? So you know that things that are near this big clump of mass right here should have an inflow around it. So you could actually use basically linear theory to just do a reconstruction of the large-scale velocity field. And if you then have reconstructed the large-scale velocity field, you compare that with your estimate of V that you got from the previous slide, and the amplitude of that is telling you something about how many electrons there are caught up in those bulk flows. So you're learning about the relationship between galaxies and electrons by doing this comparison. All right. So this turns out to be technically a galaxy-galaxy temperature bispectrum. So if you wanted to do it in the language of non-Gaussianity, you could just do a GGT bispectrum and do all the calculations. But I find it easier to think about this as this cartoon. All right, so we now have a way to estimate how electrons are associated with galaxies. What can we do with that? Well, what I would like to do with it is detect helium reionization and actually measure how helium got ionized. So, here's the history of the universe. So there was a Big Bang, I guess. There were the Dark Ages, and there's lots of talk about hydrogen reionization in the first galaxies. And at that point, you have a lot of stars ionizing things, and it tends to be the case that the first electron gets pinged off of helium when hydrogen gets ionized. Those two things happen very close to each other. However, that second electron is down deeper in that potential well. It needs a harder radiation field. And generally, it's thought that you need the quasars to actually have enough high-energy photons to get that second electron out. Okay. So if you need to get that second electron out, you're going to need a harder radiation field. So this is typically happening somewhere around like a redshift of 4. And so what that means is that when this happens, suddenly the number of electrons that is associated with a galaxy is going to get incremented by that extra helium electron. So you had all the electrons from your hydrogen got knocked off, plus one of the electrons from each helium. At a redshift of 4, you get one more electron per helium. And that turns out to be a non-trivial effect. You can see that it actually takes This XE is basically per hydrogen, is the electrons. So you go from being 1.1 electrons per hydrogen up to 1.15. So you're actually getting a jump in the number of electrons per helium, or per hydrogen. And so that's something that we can measure with this Kinetic SZ tomography. So what we should see is you should see that the galaxies at a redshift of 5 when have a higher correlation between the velocity and the galaxies. It'll be a lower correlation here and a higher correlation here because you have just more electrons caught up in the bulk flow. So basically, we should be able to use these CMB measurements to reconstruct helium reionization. That's the plan. So if someone has a model for this, so these are models, so we got these from Paul LaPlante. So he's done a lot of stuff on helium reionization, but there's actually not a lot of literature out there with detailed models for this. All right, so one last one. I'll just show the cartoon for it, and then we'll be done. So here's the last cartoon. So we can do the same thing, except with temperature, we can do something similar with polarization. So now we have the same clouds of electrons caught up in a bulk flow going this way. And now when the CMB scatters off these clouds, you're going to actually end up with a little bit of excess polarization in this direction at the locations of all of these clouds. And so Thomson scattering of the isotropic CMB by a moving cloud of electrons induces polarization. So you do the calculation. This is a tiny effect. So in terms of screwing up the search for gravitational waves, it's not really a foreground to worry about, but it is there. So just because it's not going to contaminate the CMB polarization as a foreground, though, it doesn't mean it's not measurable. And the thing that makes it measurable is that it actually has a non-CMB spectral dependence. So this is the spectrum as a function of frequency, and it goes, when you go from, say, up to 400 gigahertz, you see it's almost a factor of 3.5 or 4 higher. So it actually has this rising spectrum as a function of frequency that you can just calculate. And what that says is that you actually have some hope of being able to dig it out from all the other CMB signals. So it's worth going after, but it's very small. But what's nice about it is that you can get a template for this from large-scale structure. So if I have two sets of, this is large-scale structure, this is large-scale structure. If these two things are infalling towards each other, if you were to point a perfect CMB telescope at them, you should actually be able to see these little correlated clouds of polarization that are all oriented in this direction, and those should be correlated with these clouds in a way that's set by that large-scale velocity field. So you have a template to go looking for. All right, and we could use that to measure cosmic birefringence, but I'm out of time. All right, so there's the summary. So there's these deep millimeter wave surveys going on, and there's lots of astrophysics to do with them. So the obvious stuff like clusters and AGN and things like that. So there have been sort of a generation of people working on those, but I think it's fun to think about what's coming next. So what we can do with these CMB lensing maps, so the fact that we have all the mass between us and last scattering at reasonably high signal noise. So there must be something good to do there where we search for these hotspots, as Ito was suggesting. And then we have these flares going off. So who knows what's going on there. So the same thing is also happening with AGN. So on longer time scales, we have all sorts of, a lot of those bright spots in the map are actually flickering at a sort of surprisingly large level, like factors of 5 and things like that. Now, what's on the horizon, so especially for, say, Simon's Observatory, so that sort of next generation is KSE tomography. And so people are going to be using this to do all sorts of various probes of the electron distribution. So one example that I talked about is helium reionization. But there's no doubt lots of other things you can do with that. So if you can think of something interesting about the electron distribution, KSE tomography could be interesting. And then polarized KSE, I think I'm going to have to probably be cryogenically frozen, but we could do something with it someday. All right, so that's it. I'll take questions. Yep.
If we use your spectral index and extrapolate to gigahertz frequency, wherever the FRBs are measured, do you think some of them may be associated with your flares or not?
So definitely the FRBs. So what do I know? I know that if you take the FRBs and if you give them a flat spectrum up to 150, then we have a tough, that's right about, so the brighter FRBs, if they had a flat spectrum, would be something that we would have a tough time detecting at 150.
So it's a different population.
The time scale.
The time scale
The
is
time scale is much longer, but maybe at low frequencies it's brief.
Yeah, so, right, but then,
Above the threshold of detection.
but what I just said was for a flat spectrum. So what that means is if it actually was a rising spectrum, then that actually would, like the energetics would work out, even though the timescales are wrong.
And are they concentrated in the galactic plane, or you have them all?
Oh, we don't look in the galactic plane.
Oh, so, I mean, obviously, it could be in principle, yeah.
I mean, we're actually starting to look in the galactic plane now, just to see what we see. They're definitely cosmological. Well, the stars are not cosmological. The stars are nearby. Like, we have Gaia counterparts and things like that. So actually, that's the whole thing, right? Is we have Gaia counterparts to these things. These are just stars. They're nearby stars.
Right. The only question is whether there are other stars that produce some flares. They are.
So if this was outside our galaxy, yeah, there's no way we would just, if you just took an FRB, they would not look like this. But it's good to think about. Like, it is a real question is whether we should be looking in our data for FRBs. Because as I said, like if you just do a flat spectrum, then they should be just barely detectable with like 3 years of a grad student. So is that a good use of 3 years of a grad student? It's just like flat spectrum, it's like, you know, it's 3 years later and then you say, well, I guess the spectrum is probably not quite flat, it's probably falling a little bit. And I don't know how the grad student's gonna like that. But if you see them, it'd be amazing. So I think the better thing to do is, so like ACT or Simon's Observatory that's coming up, they actually have overlapping sky with, say, CHIME or an FRB dedicated survey, and they actually know, like, so CHIME is just drift scan, it's just looking up. So it'd probably make more sense for someone to just do some synchronous survey with an actual FRB experiment over the same patch of sky, and then just try to catch objects in common. And then you can go down to lower signal noise in your detection thresholds and things like that. Because if you actually know that it's a real FRB, then you could just stack your map on that spot. So I think that's a better way to do it than just look for it in our data. And, yeah.
So I haven't followed the literature, but has the kinetic SZ effect actually been seen in clusters? I know 10 years ago when I checked, they said, it's all iffy.
It's definitely been detected.
And
So
everyone agrees.
Yes, yeah, 100%. Everyone agrees it's been seen. Now it's hard to see it in individual clusters so much, and it's actually something that I think it took a long time for people to realize this, which is that if all you care, and it's the same thing with lensing. Like lensing of the CMB, people initially talked about measuring it around clusters, but eventually someone realized that, oh, wait a second, there's a tiny fraction of the mass in the universe is in a galaxy cluster. So why not use all the mass in some region instead of just that little bit in the center? And it's the same thing with the KSZ. So what people have done is they basically detected it by looking at correlations between the CMB map and so it was first detected with pairwise galaxies. You just look for galaxies that are infalling, and then so if they're infalling, then the back one you would see is going to blue shift stuff, and the front one's going to red shift stuff. So if you just do like the back one minus the front one, then that actually is giving you an estimate of that pairwise velocity. And if you just stack that pairwise velocity over galaxy pairs, then you see a big signal. So ACT did that first. So SPT's done it as well. Planck has done it. So that's been detected at high signal noise. Individual clusters, I would say people still argue about that. I think Planck says that they've done it with individual clusters. But it's just harder because it's a one-off and you have to worry about what emission is coming from the cluster itself.
I think we'll have to stop here, but there's still time to sign up. You want to discuss further with Guszejnov?
simulation.